So are we good? Can we go ahead? Great. So I'm Gianni.
And I'm Julio.
And today we're here to talk to you about SVT-AV1-PSY. So to introduce this project, SVT-AV1-PSY is a fork of SVT-AV1 with some perceptual and quality of life features. So today we're going to talk about why we started working on it, some of the technical implementation details, and the current state of the project. So the reason why we started doing this is because there's been a trend over time in how encoders are developed that wasn't super favorable to psychovisual features. So initially, right, X264 was developed by Videoland in the community, and now we see SVT-AV1 developed by Intel, Netflix, and Meta, now mostly Meta and Intel. So between X264 and SVT-AV1, development has shifted from a highly perceptual focus, right, like focused on the human visual system, to a focus on metrics. And this has not resulted in a lot of community satisfaction with AV1 encoders. So LibAOM is flexible. You can do a lot with it, but it is very slow and benchmaxed, right? So kind of overfit for objective metrics. SVT-AV1 at the time, right, was very fast and very good at metrics, but still overall pretty benchmaxed. And targets the arithmetic mean of PSNR, SSIM, and BMF. So Ravi, I think I personally liked the direction Ravi was going very much, but the development momentum started to slow down compared to other open encoders, and LibAOM forks that were floating around at the time were not very well maintained, and the features had, frankly, very dubious value. So it was clear that if nothing changed, the best open AV1 encoder wouldn't have many psychovisual features. So our idea was, like I mentioned, the state of LibAOM forks was unfortunate, and the way in which it was unfortunate was pretty bad. So they had messy commit histories because they weren't rebased properly on mainline. They had a completely inscrutable release cycle where occasionally someone would say, hey, there's a new release that's very cool. Here's a patch that I'll send you over Discord, and you can apply it to the code base yourself and build it. And sometimes there were patches on top of patches. It was great. And there was also no relationship whatsoever with the Upstream project. So our idea was to properly bring back community encoder development in a way that we thought made sense. So the first step was to recruit the devs from the LibAOM forks. I think what they wanted to do was very good. It's just often lack of resources, and it's one person at a time. It's very hard. We wanted to build a team with those people, engage the community with new features, and make things that people wanted to use and were excited to use. Part of that was also having a release cycle that was mainline compatible, so we could rebase on mainline very easily, and our releases were distinctly different and interesting. We wanted ergonomic features as well that made sense to people who were not necessarily encoder developers, and we wanted an active public presence that would eventually lead us to a relationship with the mainline team. So we forked SVT-AV1, called it SVT-AV1-PSY, named after the first LibAOM fork called AOM-AV1-PSY. And I started work in January with two other people, Clivius and Blue Sword M, who were working on LibAOM forks. Julio came on soon after that.
All right, so about features. During the lifetime of SVT-AV1-PSY, we had 13 releases since launch from February 2024 to April 2025. We have 20 plus impactful features and 388 GitHub stars. We also have a fun website at svt-av1-psy.com. You should go check it. And these are the major features we'll talk about today. There's a variance adaptive quantization, which is also called variance boost, the extended and quarter step CRF, AC bias, and tune 4, which is still picture. So variance boost is a variance AQ implementation that was adapted to use AV1's delta Q signaling. It was actually initially an SVT-AV1 patch. This actually predates SVT-AV1-PSY. So it actually became SVT-AV1-PSY's first feature. So what variance boost does, it helps retain vein textures, so most notable skin, and improves low contrast scenes, like dark scenes, foggy scenes, overexposed scenes. It can also be used together with other delta Q modes. For example, SVT-AV1's TPL, which is like the temporal AQ, which is really nice. and it's also optimized for various kinds of content. For example, SDR and HDR video and still picture. And one thing that is like pretty unique for Variance Boost is that it always uses 64 by 64 super blocks, which are the smallest ones. And this is because the finer quantizer granular control is like always like worth it over like the total signaling overhead during like our testing. So here's an example where like these are two bitrate matched pictures, and you can see the one with Variance Boost on, it basically retains skin texture much better than the one without Variance Boost. So for extended and quarter step CRF, so it's basically an issue with SVT-AV1. So in order to encode things with CRF, it basically there are 64 QPs, but those lack granularity, which means basically like there's like a 7% size difference between consecutive values. And that highest CRF, which is 63, can sometimes result in too large files in some cases. So the solution was to extend CRF from 0 to 63 to 0.0 to 70.0 in quarter step increments. We've also made it that the new granularity, so a quarter step of a QP roughly matches 1 Q index. And for CRFs greater than 63, we basically compress the QP scaling and bias RDO towards increased bit saving. And you see on the graph on the right, we basically, we can now achieve MPEG codec bitrate range versatility. So we can go as low as we want to. Is it practical?
So AC bias is very similar to X264 and X265's PSY RD, or psychovisual rate distortion. So lower strengths help retain sharpness, while higher strengths can help retain scenes with complex motion or film grain. And here we have a demonstration where at AC bias strength 0, you can see it doesn't really look that great. It's kind of flattened out, and you can see some block errors, where at AC bias strength 4, it looks a lot more like the source, which has this grain detail. So the human eye doesn't necessarily care, right? Like whether or not the grain detail is faithful, it just cares that there is visual energy present where there was in the source, versus like an objective metric like PSNR might care more about whether or not we are closer to the average value of the source, so it smooths things out. So the intuition behind a feature like this, we use a Walsh-Hadamard transform to go from the pixel space to the frequency space, and then you compare source pixels to the recon after transforming. So that gives you your sum of absolute transform differences, which is essentially frequency domain error. So then, like normally what you would do in loop is compare pixels with sum of absolute differences, which is like essentially PSNR, right? So our frequency domain error here with sum of absolute transform differences still has a DC component, which is that low frequency component. So we can subtract the sum of average differences to account for this. So essentially, subtracting the transform differences, or subtracting the SAD from the SATD will give you an energy distortion number that you can use in loop. So you can scale this based on, right, like that's essentially what we do with the strength value, is scale this, and this will bias the in-loop distortion metric toward visual energy. So there's some additional things we did here. We have different weights for different temporal layers. We calibrated it so that strength equals 1.0 makes sense, and this was part of the push to have ergonomic features where a new user can set it to 1.0, and that's probably going to be the best value overall for most use cases, and it's enabled by default. So I'll try to race through this one in the interest of time, but still picture was a new tune that we introduced. So for the first time in a while, like since VP8, I guess, we have a video codec that is also an image codec. Very interesting. The approach, right, for a while has been like, build a good video encoder and good images will probably come out of it because it's good at videos. Videos are a bunch of images. So we can actually just test this. We have good perceptual metrics in the image world, like Simulacra 2 and Butterolly, which are highly perceptually correlated and useful. So Tune 4 is 5 features in one. New quantization matrix scaling curve, deblocking loop filter sharpness controls, new variance boost curve, screen content detection improvements, and tweaks to the lambda. So all Tune 4 features were optimized around the CID22 validation set and measured against other image datasets later. So we show some numbers on other image datasets. They were not optimized around those datasets. They were optimized around another one, and we used the other numbers for validation. So the first thing we did is, okay, how good are we by default with AVIF? Here's how we look against, or how we looked against mainline SVT-AV1 in their Tune SSIM and Tune PSNR modes versus our defaults at preset 4. So, you can see that we actually look pretty good here, and the metrics reward our features, which is important. It means that we have some level of validation that what we're doing makes sense. So quant matrix scaling, AV1 has different levels of quantization, or can specify different levels of quantization to frequency components. And there's 15 predefined QMs by default. So, we measure an RD curve at each QM and pick the best at each section of the RD curve, and you can either have a conditional or a polynomial that picks the best QM based on where you're targeting in fidelity. And the result here was better multi-scale detail preservation, and you can see better convex hull. The second one, DLF sharpness. The deblocking loop filter controls how the boundaries between blocks are handled. So we actually implemented controls for this to control the sharpness of this. So, try each one, figure out which one is the best. This is where we started to see video features deviate from image features, where video, a smoother deblocking loop filter might end up helping interframe consistency. But here, our image metrics on our data set very much favored the sharper settings. So we ended up landing on like 6 or 7, which was close to the max.
So for the new variance boost curve, we developed a new curve for still images. So for this curve, we had 2 main takeaways. So we didn't boost low variance as eagerly, and we tapered back high variance boost more gradually. This helped with our 10% lows, which helps encoder consistency across images. And there were also some subtle improvements in intra-image consistency and texture retention. So for this tune, we also developed a new screen content detection mode, which is anti-aliasing aware. So basically the old algorithm that was inherited from Liberium, it wasn't very effective on images. This is because it was a naive algorithm that was based on total color counting on 16 by 16 regions. And this was really bad at detecting screenshots with anti-aliased fonts, which is pretty much most screenshots by now. And the new algorithm is anti-aliasing aware, and our detection rate increased for screen content detection. And you can see on the graph on the right, it was a really big win for our custom non-photo data set, like sometimes up to 50% gains.
So the lambda is a Lagrange multiplier in rate distortion. So the cost in loop of any decision is determined by distortion plus lambda times rate. So a high lambda, you ramp up the lambda, it means you're prioritizing rate reduction in loop. And if you lower it, it means you're prioritizing distortion reduction. And I think that makes some intuitive sense because it's multiplied by rate. So for our still picture tune, higher and lower quantization, we found that decreasing the lambda was the best for our RD curve. And in between, we wanted to increase it, and that ended up making sense. So this reduced file sizes and preserved subjective quality, which is, that means better efficiency. And you can see here on our RD curve, it's kind of close, but the dotted line is the old and the blue line is the new. So initially, I showed you some results of our defaults versus SVT-AV1 in its defaults and with Tune 2. Here, we compared against other image compression or other image encoders to determine how we looked, and we tried to pick the best implementations that we knew of. So that would be Google's JPEGly for JPEG, the JXL's CJXL for JPEG XL, and AOMEG for AVIF, and we tuned AOMEG to make sure that it performed the best that it could with some custom settings. And our determination was that we had the best image encoder available and that this was state of the art. So perceptually, we also validated that the results looked just as good, and we actually made some trade-offs to the metrics for some edge cases that we found to improve perceptual quality. And this is a simulacra 2 graph, but Butterolli and DSSIM, 2 other perceptual metrics, also look pretty good for us. So we eventually wanted to merge this, and this ended up being merged to SVT-AV1 as Tune 3, or Tune IQ for image quality. It also made it to LibAOM. Thank you, Julio.
Alrighty, so you may think, okay, we made all of these improvements in a fork, and there's like a limited subset of enthusiasts who use this, but like, what about everybody else who uses mainline? So we decided to end up like merging as much as we could to mainline SVT-AV1. So started with the work to merge that code, and this happened in 2 waves. So the first wave was done by Gianni in December 2024. And the second wave was done by me. This was pretty recently, September, October 2025. We just like finished the second wave. And a few features were upstreamed by other community members, which is really cool. We got like community engagement there. We also discussed like the contribution plan with the SVT-AV1 team, and the interest, collaboration, and feedback that we received was really outstanding. It was like really good. And all of this work was tracked in this issue 2269 on GitLab's SVT-AV1 mainline project. And like you can see on the right, it's basically like a checklist of SVT-AV1-PSY features. And by now, like, we pretty much like merged like the most important things. So there are other notable PSY features that made it to SVT-AV1, which are QP scaling compression, frame luma bias, adaptive film grain, the max transform size, odd resolutions, and less than 64 by 64 input support, dynamic delta Q rest switching support. And this is a fun one. We actually got a detailed and colorful progress report, as you can see on the screenshot below.
Very important.
Yeah, very important. Because we also had fun while doing this. And there are many other more PSY features. So, yeah. So our work didn't like stop at SVT-AV1. There were also some LibAOM improvements that were the result of PSY. So the most important one was the entire TuneIQ feature set was ported over to LibAOM. And you can use TuneIQ by using that AVIF command to invoke it with TuneIQ. And we want to try to make this even easier, like by making TuneIQ default in libaif. And I think we're getting pretty close to that goal. The ETA is January 2026. And there's some cross-pollination as well, because some of the improvements that came from libaim were later ported to SVT-AV1. And these are, like, most notable, adaptive DLF sharpness, a fast mode for anti-aliasing aware screen content detection that saves us a bunch of milliseconds, which is very important, and inter-block copy block hashing performance improvements. And all these improvements didn't even stop at AV1. It turns out that the work on TuneIQ actually helped improve AV2 coding tools for future still picture tuning. So we worked on 2 proposals. So there's a quantization matrices coding for AV2 and the delta Q entropy coding optimization.
Thank you guys so much. I personally wanted to shout out Blue Sword M and Clivis, who are not here, but they were 2 other members of the core team that we worked with over the time that we built SVT-AV1-PSY. And these community contributors as well stepped in. Some of them we don't know, they just submitted code, and we very much appreciate that. So thank you guys so much for listening. Do we have time for questions? I'll take that as a yes. Are there any questions? Sure, right up in the front.
In your AC boost, you add noise, let's call it, a variation in it, based on how much there was previously. Have you stopped dots crawl or equivalent between frames? Because sure, you said you add. Say you had green, you go light green, dark green, light green, dark green, which doesn't necessarily match what was on the original, but the energy is the same.
Right.
How do you make sure that that's the same on the next frame, in the same position on the next frame, so that when you have motion, your dots don't sort of crawl across the screen?
I guess biasing the in-loop metric toward visual energy just lets the encoder make decisions that preserve visual energy irrespective of considerations like that. So I would say it's probably up to chance. I don't believe we've seen that issue happen very often. Just because, right, like it's choosing prediction modes, for example, that favor visual energy and not really doing much more. I don't know if you've seen anything.
Yeah, so the way I see it is that we're at a point where, okay, we basically can control the strength of like this effect. So we know that like if you set the strength too high, some artifacts will appear. So our recommendation is that like if your content is very clean, you basically use like 0.5 to 1.0 strength. And if it has film grain, we're at the point like preserving the film grain actually is like more of a priority. Then you go into like strength 3 or 4.
You're in AV1. Why are you applying film grain at the compression stage? Sure, it's a pass afterwards if you're doing conformance.
So there's a question because like AV1 has film grain synthesis, right?
Yeah, mandatory.
Yeah. So there are some limitations from using FGS, especially like the very high bit rate. Whereas like there are some cases where it's like a very large grain where FGS is not able to kind of match the same look that like something that film grain preservation does. So this is like one of the main motivations for us to actually retain the original feel of the grain versus like just like wipe it off and apply FGS, which is like some strategies like that companies like Netflix uses.
We have features to improve film grain synthesis, and I think making the argument that film grain synthesis is perfect is a hard argument to make. So there were a lot of cases in which preserving the original film grain with the coding tools beyond film grain synthesis actually ended up helping perceptually. So that was right, like our whole development cycle was just like, if it helps perceptually, we will implement it and make sure that it sticks around. And you know, you can compare, like SVT-AV1 had film grain denoising on by default, so you know it applied 2D denoising and then applied film grain, and that was disabled because it didn't look very great. So it's clear that these things are all in progress, but can film grain synthesis be better? Yes, probably. Can it be better than what's in AV1? Probably, right? So I think it's still an ongoing problem, I guess.
Yeah, so it's all about like developing a tool set and just like choose the right option given the bitrate constraints.
Any other questions? Over there.
From memory, I had a quick look on my phone. X264 used SAT-D plus SAD for its AC bias, I think, but I was only a quick look on my phone. Is there a significance with your minus plus the, I might be looking at the wrong metric, but is there a significance with either plus or your minus?
I don't
So,
know. Is that true?
So like, I haven't looked at the X264's implementation. So this was like closer to the X265's implementation, which it's like closer to what we have in AV1 in terms of like block sizes and prediction modes.
Because also the intuition, right, is you have a Hadamard transform, which still has a DC component. And I believe if you read like, you know, the older documentation on how SIRD works, like, you know, subtracting SAD essentially just eliminates the DC component so that you only have AC error. That's as far as I understand it. Maybe there's other stuff happening, but that's what we have, and it seemed to work quite well.
And there's always like a possibility of refining the actual energy gap metric.
Are we out of time?
Yes, you are.
Okay, thank you very much. Right.
맞아서.